Hello and welcome to mathandsciencepower.com. If you like what you see here, please remember to subscribe, comment, rate, and share. Okay, chapter 16, problem number 6 says, particles of charge positive 70, positive 48, and negative 80 microcoulombs are placed respectively in a line. The center one is 0.35 meters from each of the others. Calculate the net force on each charge due to the other two. Okay, so I'm going to start out by drawing a picture here, and we know that we have a positive 70 microcoulomb charge. We have a positive 48 microcoulomb charge, and then we have a negative 80 microcoulomb charge. Okay, and the center charge is 0.35 meters from each of the other two. Okay, so for the purpose of this problem, I'm going to let D equal 0.35 meters. Okay, so the problem asks us to calculate the charge on each of the three charges. Calculate the force on each of the three charges caused by the other two charges. So we're going to need Coulomb's law. We need to know the force. So the force between two charges equals K, the proportionality constant, times the charge of the first particle, times the charge of the second particle, divided by the distance between them squared. Now this works if we have two charges, but here we have three. So what we're going to do is let's call this Q1, we'll call this Q2, and we'll call this Q3. So we're going to start by finding the net force on Q1. And to do that, we need to find the force between Q1 and Q2, alright, sub 1, 2, and then we'll need to add that to the force between 1 and 3. Okay, so Q1 and Q2 are both positive. These are going to want to repel. But Q1 and Q3 are opposite sign. This one's positive and this one's negative, so they're going to want to attract. So what we're looking for is the net force that Q1 wants to actually do. So before, when the charges were the same and then the force came out to be positive, we said that that was a repulsive force. And when the charges were different, the answer came out to be negative, we called that an attractive force. But in this case, we want to do something a little bit different, make it a little easier. We want to let the left direction be negative, and we want the right direction to be positive. Okay, and this will just help us keep everything in order. So let's look at the force between 1 and 2. Okay, we're going to start out with K. We're going to multiply by Q1, Q2, and then we're going to divide by the distance between these two squared. And then we're going to add the force between 1 and 3. So that's K again, Q1, this time it's Q3, and this time the distance is actually twice D. Okay, so D is only the 0.35, but we need 0.7, so that's going to be 2 times D, and we'll square that. Okay, so before I plug any of my numbers in here, I'm going to go ahead and factor this. So the force on Q1 equals, and let's look at the common things that I can take out here. Both of these have a K in them, they both have a Q1, and they will both have a D squared. Okay, so 2D squared is the same thing as 2 squared times D squared. In other words, the square of a product is the same thing as the product of squares. Okay, so this will simplify to 4D squared. So I will have a d squared here to take out also, and I'll be left with a 4. So I'm going to start by factoring. we will take out the K, the Q1, and the over D squared. And what we are left with is Q2 plus, and here I'll have Q3 over 4. Okay, so now we can look at plugging in some numbers. Okay, so let's just recall that K is 9 times 10 to the 9th Newton meters squared per Coulomb squared. So that's what we're going to plug in for K. 9 times 10 to the 9th Newton meters squared per Coulomb squared. Q1 is 70 microcoulombs. And I'm going to use times 10 to the negative 6th. That's the same thing as micro. And then we will divide by D squared. So remember that D is 0.35 meters. Okay, squared. And then I need to multiply by Q2 plus Q3 over 4. So Q2 is also positive. So when these two react with each other, it's going to want to cause Q1 to go to the left. That's the negative direction. So here I'm going to, when I plug this in, I'm actually going to plug this in and call it negative 48, only because the force is going to want to go to the left. So I want my force to come out to be in this left direction, and I need it to be negative to do that. So I'm going to do negative 48 times 10 to the negative 6th coulombs plus, and then in this case Q1 is going to want to go to the right because of Q3, and that's the positive direction. So when I plug this in, I'm actually going to plug in positive 80 microcoulombs. So I'm not plugging in the numbers based on what their charge is, whether they're positive or negative. I'm plugging them in based on what direction Q1 is going to want to go. So that's how I'm determining whether it's positive or negative. So we're going to use positive 80 times 10 to the negative 6 coulombs. And this is going to be divided by 4. Okay, so the net force on Q1 will be, and I'm going to start out in this set of parentheses, and I'm going to start out with this fraction. I need 80 with an exponent of negative 6, and I need to divide that by 4 equals, and then I'm going to add a negative 48 with an exponent of negative 6. So plus 48, but that's negative, with an exponent of negative 6 equals. Okay, now I need to multiply by 9 with an exponent of 9. And then I need to multiply by 70 with an exponent of negative 6. And then I need to divide by 0.35 squared. Equals. And you see we get negative 144. So the force will be negative 144. And let's take a look at our units. Here we have meters squared in the denominator and meters squared in the numerator, so these will cancel. Here when I take coulombs and I add it to coulombs, I'm still just going to get coulombs. But then when I take coulombs and I multiply by coulombs, then I'll get coulombs squared, and that's in the numerator. And here I have coulombs squared in the denominator, so these will cancel. And I'm going to be left with newtons, which is good because we want our force to be measured in newtons. And the negative tells us that the direction of the force on Q1 is to the left. We got a negative answer. So the repulsion between these two is greater than the attraction between Q3 and Q1. So Q1 will actually want to go to the left. So I'll just write here that the force on Q1 is negative 144 newtons. And so now we need to repeat the procedure, except now we need to find the net force on Q2. So the force on Q2, and we're going to do the same thing that we did before. We need to find the force between Q2 and Q1 and add that to the force between Q2 and Q3. So we need to know the force between 2 and 1 and add that to the force between 2 and 3. And again, we're just going to use Coulomb's law. So the force between 2 and 1 is going to be K times Q2 times Q1 divided by the distance between them squared, and then we will add K, Q2, Q3 and divide that by the distance between them squared. So this time note that the distance between Q1 and Q2 is equal to the distance between Q2 and Q3. Q2 is 0.35 meters from either of the other two charges. So here I'm just going to use D for both. Okay, so the force on Q2 equals, and I'm going to factor again. I've got the K, the Q2, and the D squared in each of these to factor out. So that's K, Q2 over D squared. And what I'm left with is Q1 plus Q3. So now I can go ahead and start plugging in my numbers. K is 9 times 10 to the 9th Newton meters squared per Coulomb squared. And Q2, if you recall, was 48 microcoulombs. So I'm going to use times 10 to the negative 6th. And the distance is 0.35 meters. And we have to square that. And then we need to do the same thing and determine the directions. So when Q2 is acted upon by Q1, they're both positive, so Q2 is going to want to go to the right. So now this time I will enter 70 as being positive. Okay, so Q1 in this case is going to be positive 70 microcoulombs times 10 to the negative 6th, and then plus, and now Q3 is negative and Q2 is positive, so these are attracting. So again, Q2 is going to want to go to the right, it's going to want to go toward Q3, so that's still positive. I'm going to enter this number as positive again, so this is going to be positive 80 microcoulombs. Okay, and then let's see what the force will be on Q2. So I'm going to start again here. I'm going to add these together. I have 70 with an exponent of negative 6. And I'm going to add 80 with an exponent of negative 6 equals. And then now I'll multiply by 9 with an exponent of 9. I will multiply again by 48 with an exponent of negative 6. And then I will divide by 0.35 squared equals. Okay, and here we get, I'll just round this to 529, and it's positive. And of course our units, meters squared will cancel meters squared. It's the same setup as before. We'll add these together and still get coulombs. Coulombs times coulombs is coulomb squared. That's in the numerator. Here I have coulomb squared in the denominator, so these will all cancel. And we're left with newtons, which is force. Okay, so positive 529 newtons. So Q2 was positive 529 newtons. And again, positive is to the right this time. So these repel, it wants to go right. These attract, it still wants to go right. The net force is to the right. Now we can do the exact same thing for the last charge. So we'll start again with the net force on Q3 will equal the force between 3 and 1 plus the force between 3 and 2. And again, the force is, by Coulomb's law, K Q3 Q1 divided by the distance between them squared plus K Q3 Q1 divided by the distance squared. But remember that Q2 and Q1, the distance between them is twice the distance between Q2 and Q3. So we'll want to make sure that we write this as 2 times the distance and then squared. Okay, and again we'll factor. Remember that 2d squared is the same as 4d squared. Okay, because of the parentheses. So we'll go ahead and plug in our numbers. Okay, I'm sorry, we'll factor. Factor out the k Q3 over the d squared, and we will be left with Q1 over 4 plus, I'm sorry, this should be Q2 plus Q2. Now we'll plug in the numbers. Okay, so K is 9 times 10 to the 9th Newton meter squared per Coulomb squared. Okay, and Q3, if you remember, was 80 microcoulombs. Now it was actually negative, but I'm not going to enter the negative this time based on the charge. I'm going to enter the negative only based on the direction. And Q3, the directions depend on Q1 and Q2. I'm going to leave Q3 as positive. Okay, and D is 0.35 meters squared. And then we will multiply, and Q1 was 70 times 10 to the negative 6th coulombs over 4 plus, and Q2 was 48 times 10 to the negative 6th coulombs. But let's look and make sure we've got our directions right. Okay, so Q3 is negative. It's going to be attracted to both of these because they're both positive. So in both cases, Q3 is going to want to go to the left, and that's the direction we're calling negative. So in the formula, I'm going to enter both of these as negative. Okay, I want this to be negative, and I want this to be negative. Okay, so the net force on Q3, and again I'll do what's in the parentheses first. We have, I'm going to start here with this fraction. We have 70, it's negative, with an exponent of negative 6, and I'll divide by 4. And then I will add 48, but that's negative, with an exponent of negative 6. And then I will multiply. So times 9 with an exponent of 9 times 80 with an exponent of negative 6, and then we will divide by 0.35 squared equals. And I'll round this to negative 385. So Q3 equals negative 385. And again, it's the same situation with our units. Meters squared cancel. These coulombs squared will cancel these coulombs. Oh, and I forgot to put the coulombs here. That's also going to cancel. And we'll be left with newtons, which is force. Okay, so I get negative 385 newtons. Okay, so Q3, the force on it is negative 385 newtons. So negative is to the left. So again, it's being attracted to both of these. It wants to go to the left and get closer. So that's to the left, negative. On behalf of MathandSciencePower.com, thanks for watching.